Hello, everyone. My name is Akshay Paruchuri. I'm a computer science PhD student at the University of North Carolina at Chapel Hill. In this video for VACV 2024, I'm presenting Motion Matters, Neural Motion Transfer for Better Camera Physiological Measurement. This is a joint collaboration between the University of North Carolina at Chapel Hill and the University of Washington. First, let's talk about camera-based physiological measurement. The basic principle of camera-based physiological measurement is that light is reflected by the skin and is measured by a camera, such as a camera in your smartphone, in order to capture changes in the subsurface blood volume pulse. Typically, after a camera captures this data, further computation is done in order to extract physiological metrics of interest, such as cardiac waveforms that include the PPG, or photoplethysmography, signal. You may wonder, why is camera-based physiological measurement useful? Cameras are ubiquitous and can be found in over 6.56 billion smartphones and 1.6 billion personal computers as of 2022. Furthermore, the number of Americans using telehealth services has increased exponentially over the past years, with approximately 28 million users in the year 2022. In addition to telehealth, there are a variety of other applications that camera-based physiological measurements could be useful for, such as baby monitoring, chronic disease care, and elderly care. On the topic of telehealth, it's a rapidly growing, important field. Various news articles have shown that telehealth has become an excellent service in the post-pandemic world. Furthermore, news articles as recent as December 4th, 2023 have shown that telehealth can be essential for rural populations that are typically underserved by present-day healthcare systems. Whether telehealth or another application such as chronic disease care, applications of camera-based physiological measurement require highly accurate measurements in order to appropriately assess a patient's physiological state. Let's think of the kind of video data that is typical for neural RPG models that would power such a scenario. This is a typical RPG video that could be used to train a model in order to improve RPG for telehealth applications. As you can see, the video intentionally does not have much subject motion, and therefore does not capture the typical amount of motion diversity that would be present in more unconstrained videos. We can feed this video into a neural RPG model in order to estimate the underlying PPG signal and obtain a measure that we care about, such as heart rate. In this case, the heart rate error is reasonably low at 2 beats per minute. Now, let's consider another video that is significantly more unconstrained to showcase a reasonably natural conversation task. This video clearly has more motion than the first video. When we feed this video into a neural RPG model, we end up with a significantly poorer estimate of the underlying PPG signal, and ultimately have a higher heart rate error. This is a significantly higher amount of error that could very well compromise our understanding of a patient's physiological state. This brings up a key challenge in the task of rPPG, or camera-based physiological measurement, dealing with motion. Motion can be decomposed into a variety of semantic categories such as being stationary, rotating one's head, talking, or walking. It can also be decomposed into two distinct categories in terms of motion types, rigid and non-rigid motion. Furthermore, using an intentionally constrained dataset such as AFRL, it's empirically shown that the amount of error increases as the amount of motion increases. Existing synthetic datasets produced by parametric graphics-based approaches are capable of introducing general representative data across many dimensions, such as skin tone, lighting, and motion. Unfortunately, these approaches are computationally expensive, and the generated motion can be quite unnatural as shown here. Then the question becomes, how can we improve neural methods to be more robust to facial and body motion when predicting an underlying physiological signal of interest? State-of-the-art neural motion transfer methods are readily useful with minimal tuning. A data-centric approach would involve adding more motion diversity to video data that is reliably used for training neural rPPG models. As shown below, The source rPPG video is modified using a driving video in order to generate the augmented rPPG video on the far right side. In order to further explore this direction, we developed the motion-augmented rPPG video pipeline. For the driving videos, we chose to use the Talking Head 1kh dataset in order to augment rPPG videos of interest for the task of increasing their motion content. As a part of our exploration, an important concern came up. Is the underlying physiological signal actually preserved? You may expect a pixel-wise augmentation such as motion transfer could potentially destroy or severely degrade the underlying signal. We analyze and show that this is not the case when using neural methods. Let's consider our 3 videos of interest for an experiment. The original rPPG video, the driving video to use for motion augmentation, and the motion-augmented rPPG video. We can estimate the underlying PPG traces using a neural method and then compute frequency domain plots in order to further analyze a dominant frequency peak that corresponds to the average heart rate. As you can see, the dominant frequency peak is maintained while motion is added into the rPPG video. This means we should be able to add motion to rPPG videos while reusing the original ground truth label. If we train with these motion-augmented rPPG videos in a supervised manner and reuse the original ground truth labels, this can encourage a neural method to recover the underlying PPG signal despite the added motion noise. It's very promising that the underlying physiological signal is preserved with minimal tuning. Now we ask ourselves, can we really use motion-augmented videos to achieve state-of-the-art results? The answer is a resounding yes. We can achieve the state of the art using motion-augmented rPPG videos during training. In comparison to other state-of-the-art approaches, we observed up to 47% of an improvement in heart rate error. Additionally, we performed extensive inter-dataset comparisons in order to benchmark our approach across a variety of different datasets with diverse motion. Specifically, we trained with the motion-augmented version of the UBFC-rPPG dataset and observed up to 79% of an improvement when testing on other datasets. Then comes an important question. Is naturally sourced motion really better than synthetically sourced motion? The answer seems to be a convincing yes for both synthetic data and real-world data. Furthermore, real-world data when augmented with more motion can allow for impressive results that can reach the state of the art. Lastly, our approach is 30 times faster than existing parametric graphics-based methods to create rPPG videos. Remember this slide? It should be clear now. Motion truly matters. With motion-augmented data, there's a clear improvement across all of the motion categories. In summary, neural motion transfer algorithms can be a useful data augmentation technique for training machine learning models for the task of rPPG. As we've shown, the underlying physiological signal can be preserved using neural methods, and leveraging this observation and the original ground truth labels enables effective training in spite of added motion noise. This ultimately can produce more accurate rPPG models that are robust to motion noise. Our results include a 47% improvement versus prior state-of-the-art methods, and up to a 79% improvement when training with a motion-augmented version of the UBFC-rPPG dataset and testing on other datasets. Thank you for listening. Before I conclude this presentation, I would like to give a warm thanks to my wonderful collaborators at the University of North Carolina at Chapel Hill and the University of Washington. Through this presentation, you've heard about a promising training data augmentation for rPPG videos. Feel free to scan the QR code in the top right of the slide in order to access our project website, where you can find our paper for more details as well as code, pre-trained models, and datasets.